Then our next speaker is Sandro Villanova from Universidad de Concepción in Chile, and he will talk to us about the ancient Bulge.
Okay, thank you for the introduction. My talk will be about a project we have with a large group of people that are mentioned here. Some are from Chile, some are from Argentina, from United States, China, Italy, so a very heterogeneous group. So the project is to study the ancient bulge, that means the old part of the inner region of the galaxy. So why the bulge? So the bulge is affected by differential reddening, high differential reddening, is crowded, and for this region it was very poorly studied in the past. So it's very difficult to study this region because of all the issue with the crowding, the reddening, etc. But it is also the oldest part of the galaxy, we think. It has peculiar chemical pattern if we compare it with the halo, for example, or the disk. It has a very old and very metal-rich population, how it happened in the halo, for example. But it's still forming massive cluster today. Let's think to arches, for example, the quintuplet cluster, etc. But what is most important is that we finally have the instruments to penetrate the clouds of dust and collect data for millions of stars. We have, for example, the DVV survey, the apogee spectroscopic survey, and so on. So now, today, we have the methodology, the instrument to really study deep to this part of the galaxy. So our project is called CAPOS, the Bulge apogee survey that has the aim to study spectroscopically a large fraction of the Bulge Globular Cluster. Why Globular Cluster? Because they are the oldest object in the galaxy for which we can obtain ages, precise ages. And with that information, we can try to understand the formation history of the bulge. So we started this project in 2015 using the apogee spectrograph that has 300 fibers. And we pointed 18 Bulge Globular Cluster, plus of course, field star, K2 star, M-blanc, and pristine stars. But our main goal were the member star of each one of those globular clusters. Here you have a map with the cluster we could observe. Not all of them, of course. We observed just a fraction, but we have new observation now trying to observe all of them. So what I want to speak about in these presentations is we are investigating many subfields with this project. Well, one of them is the distance. So the distance of those clusters is a key information mainly to obtain the orbits. So to know if a cluster is a real member of the bulge or if it is an interlooper. For example, our halo cluster, this is passing through the bulge today. So it is challenging to obtain distances for sub-object because we need homogeneous distances. So we have to use homogeneous photometry, of course, proper motion for membership determination. This is a key information for those objects that are heavily contaminated by field stars. And because they are far away and they are reddened, we are limited to use only the upper part of the red giant branch. We cannot use, for example, the main sequence to obtain distances. So the ingredients, what we have, what kind of data we have to obtain distances and metallicity and reddening. We have, of course, GAIA proper motion. This is a big help. We have membership, we can separate the field from the cluster. Then, combining GAIA with 2MASS, we have a wideband photometry that help us to obtain the absorption and also the absorption law, keeping in mind that toward the bulge, the absorption law is different from the disk. For example, the absorption coefficient RV is different from 3.1, that is the value that is assumed for the disk. So we have to determine not only the absorption, but also the absorption law. That is quite complicated. And last, we have to choose a kind of isochrone models for isochrone fitting that are reliable. And we choose to use the Padua isochrone for many reasons. One of them is that they are available for many photometric systems, and they allow interpolation in metallicity. And that's why, together with distances and reddening, we want to obtain also the metallicity or global metallicity for each cluster. So using this isochrone fitting to the upper part of the red giant branch, that's all we have for those clusters, or for most of the cluster, we can get, for example, mean proper motion from GAIA. Using the apogee spectra we have for those clusters, we can have radial velocities, so we can have the full velocity space. We obtain the absorption and the reddening law through the parameters AV and RV, that are the parameters that are used in the Cardelli law for the reddening law. We can obtain also the global metallicity of each cluster that I remember you is different from the iron content, and is sometimes also different from the iron plus alpha element content. So the global metallicity is a parameter that tells us the global content of metals in the cluster, so including carbon, nitrogen, oxygen, or the elements heavier than helium, and is very often do not coincide with the iron abundance. Then we can correct also the CMDs for differential reddening for all the bands we have. So the GAIA band, GBR, and the 2-mass band, JHK. We can finally get a typical distance error of 100 parsec for each country, of course, depending on the cluster, if it is closer, if it is far away. But the mean error we have on the distance is of about 100 parsec. Having the red giant branch only, we cannot determine ages, but we just have to assume an age typically of 12 years. However, this assumption has not a big impact on the final distance determination. So now I move quickly to show you some results. This is FSR 1758. Is Moby Dick one of the most massive cluster found lately? And here you see in this CMD, you see by blue points the field stars, the gray point are the cluster stars selected by GAIA before the differential reddening correction, while the red points here are the cluster member after differential reddening correction. You see how much better is the red giant branch after the differential reddening correction. So you see, we obtain a distance using the red giant branch fitting of about 9,450 parsec. That is essentially in very good agreement with what obtained from other groups. The upper part indicated here of the red giant branch is a good metallicity indicator. Again, global metallicity indicator, and we obtain a global metallicity of minus 1.35. That is also in agreement if we compare it with the spectroscopy. We obtain absorption of AV of 2.41 and a reddening law of 2.5, so a bit lower than the 3.1 assumed for the disk. So what I want to underline here is that this CMD K versus BP minus K is the best absorption estimator, the best CMD to estimate the AV absorption. And the distance, that is the main parameter we are looking for, is obtained by several methods. For example, simultaneous isochrone fitting to multiband CMD. This is just one of the CMD we are using. Then using an isochrone, you can add also the temperature using the color, for example, and the K magnitude. So you have two ways to estimate temperature, and you adjust distance in order to have the same mean temperature for the stars. And of course, there is always the visual inspection using the sanity check things like the red RGB tip, the brightness of the horizontal branch, the RGB shape. So we use different methods to obtain distance. Some are automatic, I would say, other are like based on visual inspection. And this gives us the distance of about 100 parsec.
1 minute.
Okay, okay, I skip this one. This is another cluster for which we obtained the cluster 2012, and I would like to jump to the conclusion. If you see, okay. So using having a distance, a good determination of distance, we can obtain orbits and finally define or check if the cluster is a real bulge member or not. For example, FSR 1758 is not a bulge cluster, in spite of the fact that today it is close to the bulge, because its orbit lies outside the bulge. So it goes from a distance of 2,000 kiloparsecs from the galactic center to a distance of 8,000 kiloparsecs. So we could calculate orbits and determine that it is not a bulge cluster, while on the other hand, a final example, 2012, having the distance, we could obtain a very good orbit. The gray point are the errors. And we see that its orbit is well within the bulge area, with the distance moving from 1 kiloparsec from the center to 2 kiloparsec from the center. So this is all. Thank you for your attention.
Thank you, Sandro. Questions here from the audience?
Sorry, I have to go a bit fast, but I cannot explain every point in detail. So if you have some question.
No worries. We're waiting here to see if there's anything on the chat on the audience. I can, well, I'm not from the area, but I wanted to know, is this, you mentioned that there was an error of 100 parsecs in the distances.
Yeah.
Is this, I have no idea what the errors were before. I mean, how much of an improvement this is? I mean, with the data that you have in hand.
Okay, so how we determine this typical error? Of course, we have like a kind of benchmark cluster from the yellow, like M22 and 1851, for which we know distances from HST data, for example. So we compare our method with distances obtained from HST data, and we could check that our method works very well. And to answer to your question, 100 parsec is a very good, or a small error. Also considering that we must use only the RGBs branch. So I would say we are doing well, and also this error allows us to determine very good orbits with a small error, I would say. So we can achieve what we propose to.
Dante, go ahead, ask your question. Dante, yes.
Yes, ciao, Sandro. So you mentioned the extinction variations. Which is your preferred extinction law for this cluster?
Oh, I use Cardelli's law, the typical Cardelli's law. I know that there are other equations, but they concern mainly the UV bands. But since we are using GAIA bands that are mainly optical in infrared, the JHK to mass bands, there is not a big difference if you use other kind of laws. I know that there are an updating of the Cardelli's law, but it's mainly in the UV part.
Thank you.
Thank you, Dante.
Okay, well, thank you very much, Sandro.
Thank you.